Have you ever wondered what would happen if you fell into a black hole? Imagine yourself adrift in the silent theater of space, when you feel a gentle, inexorable pull. It's not a violent tug, not at first. It's a subtle cosmic current, drawing you toward a patch of perfect blackness, a spot where the stars themselves seem to have been erased from the celestial canvas. This is no ordinary destination. It is the universe's ultimate trapdoor, a one-way journey from which nothing, not even light, can return. You are approaching the edge of reality itself, a place where the familiar laws of physics begin to unravel and surrender to a force of unimaginable power. The mystery isn't just about the fall, it's about what lies in that silent, waiting darkness. A black hole is not a hole in the traditional sense, not an empty void you could simply pass through. Think of it more as a cosmic whirlpool of immense density. It is so massive, so compact, that its gravitational pull becomes infinite at its center. This concept was once just a ghost in a mathematical equation, a startling prediction born from Albert Einstein's theory of general relativity. He showed us that gravity isn't a force pulling things together but a curvature of space-time itself. Massive objects warp the fabric of the universe like a bowling ball on a trampoline. A black hole is what happens when that bowling ball is so heavy it rips a hole straight through the fabric, creating a bottomless pit in space-time. These cosmic behemoths are born from the ashes of giants. When a truly massive star, many times larger than our own sun, runs out of fuel, it can no longer support its own colossal weight. The star's core collapses catastrophically under its own gravity, imploding in a fraction of a second. This collapse triggers a spectacular explosion known as a supernova, which blasts the star's outer layers into space. But the core keeps collapsing, crushing itself down into an infinitesimally small, infinitely dense point. A black hole is born, yet these are not the only kind. At the heart of nearly every large galaxy, including our own Milky Way, lurks a supermassive black hole, millions or even billions of times the mass of our sun, a gravitational anchor holding its entire stellar family in a cosmic dance. So as you drift closer, what are you truly facing? You are facing the ghost of a dead star, a gravitational echo so powerful it has become a physical law unto itself. It is a region of space where the escape velocity, the speed needed to break free from its gravitational grip, is greater than the speed of light. Since nothing in the universe can travel faster than light, the black hole becomes a cosmic prison. Everything that crosses its boundary is lost to our universe forever, pulled into an enigma that challenges our deepest understanding of existence. The darkness beckons, not with emptiness, but with the crushing finality of all the matter and energy it has ever consumed, a silent testament to the raw power of gravity. Chapter 2. Dissecting the Void. Let's explore the anatomy of a black hole. To understand this cosmic monster, we must dissect its anatomy. At its heart lies the singularity. This is the central point where all the matter that has fallen into the black hole is crushed into a region of infinite density. Here, our current understanding of physics breaks down completely. Space-time curves infinitely, and concepts like space and time as we know them cease to exist. Surrounding this impossible point is the event horizon, the true point of no return. It isn't a physical surface you could touch, but rather an invisible boundary in space. Once you cross the event horizon, the pull of gravity is so strong that you would need to travel faster than light to escape. An impossible feat. It is the edge of the known universe. But a black hole is rarely a quiet, isolated object. Often it is surrounded by a swirling, chaotic inferno, known as an accretion disk. This disk is formed from the gas, dust, and ripped-apart stars that are drawn in by the black hole's immense gravity. As this material spirals inward like water circling a drain, it gets compressed and heated to millions of degrees, causing it to glow brighter than entire galaxies. This brilliant light is one of the key ways we can detect these otherwise invisible objects. It is the death scream of matter, a final luminous farewell before it plunges over the event horizon and disappears from sight forever, feeding the beast within. Sometimes not all of this material makes it into the black hole. As the accretion disk spins with incredible speed, Powerful magnetic fields can get twisted up and act like cosmic particle accelerators. These fields can capture some of the superheated matter from the disk's inner edge and blast it back out into space. These are the relativistic jets, twin beams of particles and radiation traveling at nearly the speed of light. They shoot out from the poles of the black hole, extending for thousands, even millions of light-years across the cosmos. These jets are among the most energetic and spectacular phenomena in the universe, a testament to the chaotic power unleashed at the edge of the abyss. Now let's return to your hypothetical journey. As you approach a smaller stellar mass black hole, you would experience a gruesome fate known as spaghettification. The black hole's gravity would pull on your feet with immensely more force than on your head. This difference in gravitational pull, known as a tidal force, would stretch you out, thinner and thinner, like a strand of spaghetti, until you were just a stream of atoms spiraling into the singularity. Paradoxically, if you were to fall into a supermassive black hole, you might not even notice crossing the event horizon. Its gravitational gradient is much gentler, so you could pass the point of no return intact, only to meet your inevitable end deep within the unseen interior. Chapter 3. Bending Time and Reality. Discover how black holes warp the universe. Black holes do more than just devour matter. They fundamentally warp the very fabric of reality space-time. According to Einstein's relativity, the stronger the gravity, the slower time passes. This isn't science fiction, it's a measurable effect. GPS satellites orbiting Earth have to adjust for this, as time for them ticks just a fraction of a second faster than for us on the ground. Near a black hole, this effect, known as time dilation, is taken to the extreme. If you could hover safely just outside the event horizon and watch a distant spaceship for an hour, centuries or even millennia could pass for the rest of the universe. You would essentially be looking into the future. This profound connection between gravity and time has sparked incredible theories about the possibilities hidden within black holes. Some physicists have speculated that the singularity at the center of a black hole might be a gateway to another place or another time. This is the theoretical concept of a wormhole, or an Einstein-Rosen bridge. In theory, a wormhole could connect two distant points in our universe, or perhaps even connect our universe to another one entirely. It's a tantalizing idea, offering a shortcut across the cosmic ocean or a doorway to a parallel reality. A journey through a wormhole could be a form of time travel. However, we must tread carefully here, separating established science from exciting speculation. While the equations of general relativity permit the existence of wormholes, there is no evidence they actually exist. Most models suggest that any wormhole would be incredibly unstable, collapsing the instant anything tried to pass through it. Keeping one open would require a form of exotic matter with negative energy, something we have never observed and don't know if it's even possible to create. So, while black holes offer a theoretical playground for time travel fantasies, the reality remains firmly in the realm of theory, a beautiful mathematical possibility that the universe may not have chosen to build. Even without wormholes, the questions black holes raise are profound. What happens to time inside the event horizon? Does it continue to flow forward toward the singularity, or does it swap places with space, making a journey to the center as inevitable as moving forward in time is for us? These are questions that push the boundaries of our imagination and our physics. Black holes are not just objects, they are laboratories for the extreme, places where the rules of the universe are tested to their breaking point. They force us to confront the true nature of space, time, and the fundamental structure of our cosmos. Chapter 4. Seeing the Unseeable. How do we observe the invisible? So, if nothing, not even light, can escape a black hole, how do we know they're really out there? We can't see the black hole itself, but we can see its powerful influence on the universe around it. One of the most groundbreaking methods is the detection of gravitational waves. When two massive objects like two black holes or two neutron stars spiral into each other and merge, they create ripples in the fabric of space-time itself. These ripples, which Einstein predicted a century ago, travel across the universe at the speed of light. Observatories like LIGO and Virgo are kind of like cosmic ears, listening for these faint vibrations. and that actually allows us to hear the echo of a black hole collision that happened billions of light years away. Another way we find them is by watching the stars. We can observe a star orbiting a point in space where there appears to be nothing at all. By tracking the star's path and speed, we can calculate the mass of its invisible dance partner. If the mass is great enough, too great to be a regular star or a neutron star, we can infer the presence of a black hole. At the center of our Milky Way, astronomers have tracked the frantic orbits of stars around a central point known as Sagittarius A*. Their movements provide undeniable evidence for a supermassive black hole about 4 million times the mass of our Sun, holding our galaxy together. And then, in a monumental achievement, we actually saw one. Not the black hole itself, but its silhouette. The Event Horizon Telescope, a global network of radio telescopes working together as one Earth-sized observatory, managed to capture the first ever direct image of a black hole. They pointed their combined power at the supermassive black hole at the center of the galaxy M87, which is 55 million light-years away. The image revealed a dark central shadow, the event horizon, surrounded by a blazing, lopsided ring of light from its accretion disk. For the first time, we had visual proof, a stunning confirmation of Einstein's theories and a face for the cosmic monster we had only imagined. But even as we find new ways to detect them, a perplexing puzzle remains: the information paradox. A fundamental law of physics states that information can never be destroyed. Yet a black hole seems to do just that. Anything that falls in, with all its unique information, appears to be lost forever. The great physicist Stephen Hawking proposed a solution. Black holes are not entirely black. He theorized that they slowly evaporate over eons by emitting faint thermal energy, now known as Hawking radiation. But does this radiation carry the lost information back out, or is the information truly gone? This paradox pits our two best theories of the universe, general relativity and quantum mechanics, against each other, and its solution may lead to a new revolution in physics. Chapter 5. Unanswered Cosmic Questions. What mysteries remain about black holes? We stand at the edge of a great cosmic mystery. We've detected black holes, imaged their shadows, and heard their gravitational echoes. We understand their anatomy and their profound effects on space and time. Yet, the deepest questions remain unanswered. What truly lies beyond the event horizon? Is it a singularity of infinite density as relativity predicts? Or does quantum mechanics intervene at that extreme scale, creating something else entirely, something we just can't yet imagine? The interior of a black hole is a place where, honestly, our current science fails. A final frontier for human knowledge, forever shielded from our direct observation. These questions are not just academic curiosities. The answers could unlock the next great leap in our understanding of the universe. Black holes are the nexus where gravity and quantum mechanics must meet. A complete theory of what happens inside a black hole would likely require a unified theory of everything, a single framework that can describe all the forces of nature. By studying these cosmic enigmas, we're probing the fundamental operating system of reality itself. They're not just objects in the universe, they're clues to the very nature of the universe, holding secrets about its birth, its evolution, and its ultimate fate. Could a black hole be a parent to a new universe? Some speculative theories propose that the matter compressed into a singularity could rebound in a sort of Big Bang, creating a new universe within the black hole, forever inaccessible to ours. In this view, our own universe might have been born from a black hole in another higher-dimensional cosmos. It's a mind-bending thought, one that transforms these objects from mere destroyers into potential creators, a part of an eternal cosmic cycle of birth and rebirth. While purely theoretical, such ideas show how black holes force us to expand the very limits of our imagination. Ultimately, the quest to understand black holes is a reflection of our own innate curiosity, our drive to explore the unknown and make sense of our place in the cosmos. From the first glimmer of an idea in Einstein's equations to the stunning images from the Event Horizon Telescope, our journey has been one of relentless inquiry. The darkness of a black hole is not an emptiness to be feared, but a mystery to be solved. It challenges us, inspires us, and reminds us that no matter how much we learn, the universe will always have another deeper secret waiting to be revealed just beyond the edge of what we can see.